Wie du willst, ja.
So, Achim, what was the biggest challenge for you?
Finding an idea on which you can build an algorithm that works in reasonable time.
Okay.
Problem.
And Frank, what was your biggest challenge?
Yeah, for me, it's wrapping my head around how these more or less geometric functions here work, how to calculate intersections and picture this in my head. It's very difficult for me.
Okay, thank you. Good morning. We are the guys from Germany. Good morning, Achim.
Good morning, Thomas.
Good morning, Frank.
Hello, Thomas. Hello, Achim.
Nice to
Morning,
see you.
Frank.
Are you well prepared?
Yes, of course.
Of course.
It's a nice day today.
So it starts now. So, Beacon exclusive zone.
Beacons in Sender.
Sender. You feel the ground rumble again as the distress signal leads you to a large network of subterranean tunnels. Terranean. You don't have time to search them all, but you don't need to. UPack contains a set of deployable sensors that you imagine were originally built to locate lost elves. So we are searching for elves. So let's take a look.
Triangulate stuff.
At the input.
So we need to find in a special row how many positions cannot be positions of beacons. So we need to calculate possible positions of beacons.
Yeah.
The distance calculation is by Manhattan distance. That's easy.
So let's take a look. So
okay, we got a lot of sensors and the information what is the closest beacon. So we know that there are no closer ones. Okay.
And now the input has more words.
Okay, you can remove the words and only pass the numbers. Then you got 2 pairs of numbers.
Yeah.
So, but how is the algorithm to solve this? If we know how the minimum distance to a beacon is, then we got kind of surrounding thing. We see this in the picture here. Looks like a 45 degree rotated four corner thing, and somewhere there is a beacon on the border of this area. So now all of these positions are possible beacon positions. And now if we got these from several, then there are intersection points of these 4 corner thing shapes. And then these are the positions.
Yeah.
But we would have to know how much sensors there are and how much beacons. I don't get it really. So consider we have 2 sensors and their shape intersect, and then both say the closest beacon is at also in the same position. I don't get it. To read.
Hmm. 26 positions where a beacon cannot be present.
I think you need to track. You need to track the positions that are scanned by your sensors, and
this information closest beacon is this a relative position? Because it's minus values here also. Closest beacon is at distance x equals epsilon equals, or is this an absolute position?
The closest beacon comes from the input.
Directly below the example input, there is one paragraph. So consider the sensor at 218. Closest beacon to it is at -215.
Yeah.
Wait.
So it's the first line of input. So, and which one is it in the picture?
A good question.
So I go with the next picture where it's more nicely drawn. Consider the sensor at 87. Ten. 210.
18.
Okay.
Okay, first
Now I
problem.
get it.
Yeah.
If you look into the 2D plot for the first 2D plot for the example.
Yeah.
In row 18, column 2 is an S for the sensor. And the beacon for that is 3 rows up in 15, the very first column, because that is -2.
Yeah, okay.
I don't
start at 0, 0.
Yeah. The point is in the picture, the 0 is not at 0. Where we expect the 0 is the -2. So look at the scale of the x-axis.
So
okay. It starts with I got it. So this
so
I mark
the 2 is at 4. Yeah.
Yeah. Okay.
So,
okay.
but still, there is a distress signal. I didn't understood what this means. So in the picture are the jars drawn where they should be. So this is okay. But now what to do with it? Don't get it. Okay, now I get it. On every position there can be a beacon. In our listing, there are not all beacons listed. It's only the nearest to each sensor is listed. So now we need to kind of cut out all these four corner things from the area, and then there are positions left, and on all these left positions there can be a beacon, and we need to count how much these are in a special row. This is it.
Okay, you understand the riddle?
I understood it, yes.
Then I think you can share your screen and we follow you.
Okay.
We need to cover a single row each.
Yeah, okay. So the answer is questions for a single row because the space is infinite. So if it's not a single row, then it could be infinite, the answer. But basically, so each beacon creates such a shape here. And now if we draw from each sensor creates such a shape. And if you now draw this shape for all sensors, then there are still some positions left with dots. And these dots, there can be a beacon. It's possible that there is a beacon. And now we need to count for the row 2 million. Is this? Yes. How many positions can contain a beacon now? So how many positions still contain a dot? So we cannot implement a brute force here because 2 million is too much. So we need to think about what we are doing. I guess it's not too hard, but, or is it? I don't know.
For me, it looks like the algorithm from a couple days ago. Breadth first search.
No.
No?
No, it's more of a geometric thing here.
But you're starting from a sender, and then you spread.
We do not find a path at all. There's simply no path and no graph involved here. There are no edges and no vertex and nothing like this. But I'm not really sure if I really understood it, because this 2 million thing puzzles me a bit. This does not make too much sense. Why does he ask for row 2 million? So let's have a look at the test data, what's in there. Maybe it's simply big numbers. This would explain it, and then I would be right. I have to have a look into it.
These are my test numbers, and
yeah, okay, the sensors are at fairly big positions, so they are at like 3 million, 2 million, and so on. So it's simply that it's a big input. So he wants to prevent us from using a stupid brute force, because it's millions of positions, millions and billions, and you can't do this, draw this like a picture. This makes sense. So we need to think about how can we do this. So one possible solution would be to find for each beacon the segment on the 2 millionth row, which is covered by this beacon, and then we basically can find the intersections of all these intersections, and then the size of this final intersections is the number of covered positions, and then we need to output the number of uncovered positions.
okay, there's some point I don't understand.
Okay, we got these shapes, these four corner things. How is this called in English? It's a rectangle, but not a rectangle. So let's call them rectangles. So you got a bunch of these rectangles, say 100 of them, and each one intersects the line 2 million with something. Consider this to be the line 2 million. Then these positions would be covered by this rectangle, yeah?
Yes, I understand, but I don't know how big is the rectangle.
You know this because this is here in the list of data.
Only to the closest beacon and not more.
You got one sender and one beacon, and from these 2 points, the whole rectangle is definite. Now you count the positions, or you record the positions in the line 2 million. So you got a segment, so you get for each sender one such a segment, and then you intersect all these segments. And finally, you got a number of covered positions, and this is the answer. So,
so the sender doing a broadcast goes bigger, bigger, bigger until they're reaching the beacon, and then they stop sending.
No, they just define some positions on the line 2 million where they know there's no beacon. So look, in this picture, this sender defines that in this line on these positions is no beacon. This is so, and we need to count these positions where there is no beacon in line 2 million for all senders. That's the question. There's nothing growing and nothing anything. So the trick here is to now find some algorithm how to find these covered positions. So this is a little bit geometrical, but not too hard, because it's Manhattan distance, so it's more or less easy. So now I will parse my input first. This is well. So do you got a riddle now? Or do I speak in miracle words?
100%.
Okay.
So the sensor and the closest beacon creating a rectangle.
Yeah, such an Manhattan distance rectangle thing, yeah.
Yes, and everything in this rectangle is not in our solution.
Now everything in this rectangle, we know that there is no beacon except
Okay.
this one positions where the beacon is. So, and now we need to count these positions where we know that there is no beacon, but only for the line 2 million.
Okay, then it's like game programming, how touch some two objects together.
You can picture this like whatever you want.
Yeah, I know. Then in my opinion, it's only necessary to create a frame to get everything inside.
Yeah, well, the frame cuts the line 2 million in a segment, and you need to find a segment.
Okay.
Achim, what do you say?
I think go through the sensors, get its starting point, calculate the Manhattan distance, and then go through all the fields that are covered by them, which are on the target row. Collect them into a set, and then return that. But I think you would need to exclude the actual beacons found.
I did not fully get these details, too much details. Now, I wanted to know if you interpret this riddle like I did, or if you, what is the core question of this riddle? What is it what we need to calculate here?
Well, we have intersecting fields of sensor coverage. And the question is, of those fields in the target line, for the example set line 10, for our test data set line 2 million, how many fields are scanned that just cannot contain a beacon because we know that there can't be anyone?
This. So I'm now at a parser. This is, for me, difficult how to get these clutter out of the input. So I can't even do this with. I need to train my string processing. I'm overwhelmed by this. Take out the equals and the comma. Okay. Equals and the comma. on okay. 6, 7, 10. So, yoo-hoo, my puzzle works. Now I can implement something. So,
Very good.
so how to find the leftmost position in row 2 million which intersects such a rhombus? I think it's called a rhombus.
That's
Can we do this with binary search simply?
you want to work with an array for that.
I would simply want to find a position, so I don't care for the data structure. But if we go from the sensor directly down to the row 2 million and then search to the left with binary search for the first position where it does not intersect, then we find it more or less quickly. And we can do the same to the right. And then we got a difference of these 2 points. And this is the segment we are searching for. So I will try this with the binary search. This will probably make it. So then left would be minus infinity. So it's actually 2 binary searches, one to the left and one to the right. But also we need to consider that it does not intersect at all. So, okay. So now I in the first step, I collect all my intersections, and then later in the second step, I will collect the intersections of the intersections. So yeah. Oh, this segments, left, right, both including. Yeah. So equals x. So with the term row, the epsilon variable, yeah, here it is, epsilon 2 million. Okay.
Okay, I just ran it for the first time.
Oh, nice. I need more time to sort
Result
this.
from the test data seems to match.
Achim.
That's nice.
And I have a star.
Nice.
Nice.
So it's
Amazing.
26 minutes, so this could be a good position. So it's not too fast because we discussed a lot of text, but this implementation was fast. Yeah.
Achim, can you share your screen?
I can do that.
Explain it to the world, yeah.
There's my screen. So what I did, that is my parser.
Yes.
Just doing a split around
Yeah.
signs, commas, and colons.
Parser is easy. And then?
The elements 1, 3, 5, and 7 are the coordinates.
Yeah.
For the sensor and for the beacon. That's easy. And then I go through that for a first time, filtering out the beacons that are on the target row. Because they are, yeah, we know that there is a beacon, so they don't count.
Yep.
They're removed down here. For the covered row,
Okay, that's cool.
I just collect the X values. So I go through my sensors, plot its position down to the target row.
Mm-hmm.
If it's too far away from the target row, it doesn't matter. If it's not, I plot put point to the sensor on that row to the list, and then I go left and right until the Manhattan distance is expleted.
Okay. Nice. Smart. Congratulations. Then just solve the second part.
This beacon is not detected by any sensor. Distress beacon must have accent. Okay, and there we get the enlarged values.
Yeah. Why this? Because it's the this. That. This is not good. Why is this? X. X. Okay. E. Eh, why? Beacon. It's not it. Yeah. Distance. I don't get it. I got such a simple logic, but there's some error in it.
Okay, you get it or you get it not?
I don't get it.
You
It
don't
should
get
work.
it.
It should work, but it does not.
It should work. Okay, okay, I know this. It should work, but it doesn't work. Uh,
million, yeah. Nope.
So I've got the test result for the second part right, but algorithm needs to brute force to all those 4 million lines. That might take a while.
So maybe you want to explain first part again. What do we count in the line 2 million? Which positions?
I did it that I essentially counted all positions on that line that were covered by any sensor.
So the
And
coverage of the sensor, let me ask for this. I calculate if it's covered, if the distance from this point on the line 2 million is smaller than the distance, smaller or equal to the distance to its beacon.
Smaller or equal, yes.
So that's the whole formula, and I calculate this, and for some reason it's not right. So
sum it up for all sensors that cover the line.
yeah, I do an array, and each position I mark, and then afterwards I count. So, but it's actually
and you remove the beacons on that line that you know are there.
Yeah, I do an extra loop over all sensors and beacon pairs, and then if the beacon is on line 2 million, then I remove it. So
Sounds
explicitly.
reasonable.
Yeah. So, but this still does not do the trick for some reason. But maybe that part is somehow wrong, but it looks trivial. So I will quickly share my screen to show you how trivial this looks.
Okay.
So look at this. So this is the whole thing. So I do a left bound at minus 100 million and right bound, or 10 million and right bound. So I iterate all positions from left to right, and for each positions I check if the distance is smaller than the distance to the beacon, and if yes, then I set it to true. And then I do again such a loop, and there I check if the epsilon position of the beacon is equal to my 2 million. And if it is, then I set it to false, and afterwards I count. And I get as a result 4.5 million, so this looks not too bad. Looks like a reasonable answer, but something's wrong here. Well, any idea? First I checked my distance function, but well, Manhattan distance is not too complicated. It's the two x variables and the two epsilon variables are subtracted, and the difference is the answer. So this cannot be too wrong here. X minus x, epsilon minus epsilon. Look at this thing here. I return P2 epsilon minus P2 epsilon. This should be P1 epsilon. So this explains a lot. Thanks a lot. That's what I
Doesn't
wanted
matter
to know.
in which order you are subtracting them from each other.
Yeah, but I should subtract two difference from each
Yes.
other. I subtracted P2 minus P2, and this does not make sense. So I need to subtract P1 by P2 or P2 by P1. So now something other. Yeah, okay. So this looks maybe better. This was the right answer. So thanks, Achim, for your advice.
My algorithm is still crunching through part 2.
So then explain part 2 to us and share your screen again.
But that is just my take. I'm pretty sure there's a better solution.
First
I
explain
don't
the
have
riddle.
the idea for that.
First explain the riddle.
So, in part 2, we are in search for the distress beacon, which is not covered by our sensors. But it implies that there is one position in this entire field for the sample data from x 0 to 20 and y from 0 to 20 for the actual data from up to x and y equals 4 million.
I actually did not really understood this.
There's supposedly exactly one field that is not covered by sensors.
In all the grid or only in the line 2 million or how?
You take the grid and restrict it to the range from 0 including to 4 million including. Both dimensions.
Okay.
That is a square that you're looking at. And within this square, there is a single field that is not covered by any sensor.
Okay, so we do basically the same, but for all rows, and then maybe, yeah, okay.
There is supposedly the distress beacon, and
so now we cannot use a brute force here because it's 4 million by 4 million fields, which is a lot, 10 to the power of 12. And then if we check each single field, it would be run for like forever. So
that is essentially what I'm doing.
So, but the loop itself runs like 1000 seconds, so this would be probably okay. But in each loop, we have to check all sensors, which are 30 sensors. So it's like 1000 seconds times 31. So it would be like 30,000 seconds approximated to some hours. So, but we could do this, but it sounds slow. So, okay.
And as you can see, I still didn't have a result.
Okay.
That I got right is the result from the test data set.
Okay, can we somehow speed up this loop over all positions? So for example, if you are checking position 0, 0 in the left upper corner, and then you know there's the nearest sensor is in a fairly small distance, so we can jump some positions, but does not work very well, no.
I just got an idea. Around each sensor, we have these rhomboid shapes.
Yeah.
So what if we just take the points directly outside that shape that are in Manhattan distance +1?
We simply
of
have
all
to
these sensors, intersect them, filter them, that they are inside this giant square. Probably. And then only 1 point can maybe might be left over. I'm trying that.
Okay.
So my test data worked. Just try the solution. Your answer is not right if you are stuck.
Check your distance function. Mine was wrong.
I have no distance function.
Okay. And maybe that's the critical point.
Yeah, I solved it with my UI experience,
Okay.
creating rectangles and check collision on this. I need a coffee.
This and part 2. So don't need this. So I don't this. Now I got some logic which would run fast enough, but it does not give the right result for some.
So we're still working more than an hour. What do you think about the video?
I think I'm very short before the solution, but for the video, it does not make sense to upload such a 2-hour thing where nothing happens. So maybe you can fast forward a lot of space in this video. I don't know.
Yeah, I think we can present the first solution, but for the second, we need more time.
I feel like I would solve it in like 5 minutes or so, maybe less. But I feel like half an hour like this, so I'm not sure. But it's fast enough. Now I simply have to get it right here. And it's not too difficult.
Yeah. Wait. That's, that was
Okay, then I will end this video. Thank you guys. Much luck to find a solution, and I will upload only the first solution from Achim. Thank you guys.
Thank you, Thomas.